Neutron diffraction as probe in studying nonstoichiometry and superconductivity. The advent of cuprate-based superconductors in the late 1980s and early 1990s and the superconductivity in iron-based superconductors in the first decade of the 21st century created the flurry in the research in such compounds. In some of the superconducting series, the oxygen deficiencies created a significant role, and neutron diffraction played a significant role in identifying the extent of oxygen. Many superconductors are nonstoichiometric. One such example of yttrium-barium copper oxide superconductor was described in earlier section. N. Rupp et al. Have mentioned the importance of neutron diffraction in cuprate superconductors. Their neutron diffraction data on UCO revealed that on approaching toward low equilibrium oxygen concentrations, two different structural effects occur concurrently. First, the 2O plane chain bond length increases without a significant alteration in the planes or significant vacancies on the O1 apex atom site, and second, the O4 atoms point out toward large anisotropic vibrations perpendicular to the B-axis or large static displacements from the ideal position on the B-axis. It is also pointed out that the 2O planes does not get affected on approaching low oxygen concentrations. It was further emphasized that in UCO, the whole coupled 2O plane chain system is responsible for the superconducting properties. In another study by Oshima et al., on TLSR2-2-OI, they could model the crystal structure of TLSR2-2-OI as orthorhombic. They also found that oxygen vacancies are formed along the A direction in a CuO2Z sheet, which is consistent with a superstructure of doubling of the subcell along the B direction. It was also found out that the structure involves CuO6 octahedra and CuO4 square planes alternating along the B direction by sharing their corners in accordance with TLO-ordered oxygen vacancies in the CuO2X layer as has been presented and as suggested by authors. An apical oxygen atom in the CuO6 octahedron is closer to a TLO layer than an oxygen atom shared by a TLO6 octahedron and the CuO4 plane as has been depicted in here. The oxidation state of Cu in TLSR2-2-OI was evaluated to be 2.12 from the neutron diffraction analysis. Crystal structure of TL-SR2-2-OI. Copper and oxygen arrangement on CuO2X layer in TL-SR2-2-OI. In the simultaneous addition of Cal and CuO along with di3+ substitution in non-superconducting La2Ba2-2-4-Os compounds started showing the signature of superconductivity. Rayapral et al. Used room temperature neutron diffraction in this resultant compound La2X Dix Ca2X Ba2-2-4 plus 2X Oz, or written as La 125 further in the text, and ascertain that the holes at La3+ sites are created by substitution of Ca2+ at La3+, which led to bring the two CuO2 sheets and hence induced the superconductivity in the La 2125 compound. The typical obtained crystal structure is shown in La 2125 unit cell showing the CuO layer and oxygen atom position. Tranquata et al. And reference therein in their current perspective on superconductivity, antiferromagnetism, and neutron scattering have also emphasized the importance of neutron scattering in superconductors. They underline the fact that the high-temperature superconductivity in both the copper oxide and the iron nitide/chalcogenide systems occurs in close proximity to antiferromagnetically ordered states. Neutron scattering has proven to be an essential technique for characterizing the spin correlations in the antiferromagnetic phases and for demonstrating how the spin fluctuations persist in the superconductors. While the nature of the spin correlations in the superconductors remains controversial, the neutron scattering measurements of magnetic excitations over broad ranges of energy and momentum transfers provide important constraints on the theoretical options. In a recent study on iron-based superconductor, the parent LUF as lane equals law, SM, say, ND and GD, was found to show spin density wave below 150 K due to Fermi surface associated with tetragonal structure to transform into orthorhombic symmetry. Addition of the electron into lane O, F phase or a hole in the La, SR off S layer modify the Fermi surface, thus superconductivity could be introduced. The neutron scattering study helped in calculating the electron-phonon coupling in Lao 0.87 F0.13 phase sample. The spin density wave, SDW, could not be detected. So with the help of neutron scattering experiment, it could be established that the order parameters pertaining to SDW and superconductivity are competing for itinerant holes and electrons on the Fermi surface in La O, F phase compound. Some more examples: the structure and chemical order of a Ni-Mn Guy-Heisler alloy of non-stoichiometric composition were studied using constant wavelength, 1.538 A ring, neutron diffraction at 363 K, and the diffraction pattern was analyzed. At this temperature the structure is austenite, cubic, with Fm space group and lattice constant of A equals 5.839134. The chemical order is of critical importance in these alloys, as Mn becomes antiferromagnetic when the atoms are closer than the radius of the 3D shell. In the studied alloy, the refinement of the site occupancy showed that the 4B, Ga site, contained as much as 22% Mn, that significantly alters the distances between the Mn atoms in the crystal and, as a result, also the exchange energy between some of the Mn atoms. Based on the analysis, the composition was determined to be Ni 1.91 Mn 1.29 Ga 0.8. N. Paulus et al. Have used single crystal neutron diffraction technique to understand the structural evolution of electrochemically oxidized La-2NiO4 plus delta crystals as a function of temperature in the oxygen intercalation and to better understand the disorder of the apical and interstitial oxygen atoms. The structural evidence were found not to attribute a peroxide character between the apical and interstitial oxygen atoms situated in exactly 1/4 of the F4/M unit cell. They could also reinvestigate the structural phase transition of stoichiometric La-2NiO4 crystals at 74 K. It was also observed that the symmetry changes from Bob to PCCN and remains orthorhombic down to 5 K.